Hello, once again. Um, Today we're going to talk about section 6.3. So you just got finished looking at section 6.2, which was on covalent bonding. We're actually going to revisit that in 6.5 when we talk about molecular geometry. But we're going to stop here and take a look at ionic bonding. And this is a type of bond that usually takes place between a metal and a nonmetal. Remember, it has a large electronegativity difference between the two atoms, greater than 1.7, and it's made up of ions. Remember, cations, those are our positive ions, and our anions, those are our negative ions. The cations are usually metals, and the anions are usually nonmetals. So you can see the definition here. An ionic compound is composed of positive and negative ions that are combined so that the numbers of positive and negative charges are equal. So basically what that means is if you have a positive 2 charge on an ion, you have to have a negative 2 charge on the anion. Whether that comes from two anions that have a negative 1 charge or one anion that has a negative 2 charge, it really doesn't matter as long as they're equal and opposite. And we're going to draw some structures out. There's a 3-step process to drawing these out that sort of shows the transfer of electrons. Then it actually, you actually go through and you show where the electrons are going to be transferred. And then you look at your final formula unit. Okay, so here's just a little diagram of ionic bond formation. This happens to be, like I mentioned in previous lectures, the 6.1 lecture is sodium chloride, probably the most common ionic compound there is. Here you have a sodium atom, okay, that has 11 protons, 11 electrons. It's neutral. Here's the chlorine atom, 17 protons, 17 electrons. Notice the size. These are in the same period as you go across. And we know the trend is as you go across, atoms tend to get smaller. And you can see the chlorine atom is smaller than the sodium atom because increased positive nuclear charge pulls those electrons in tighter. Okay. Now, sodium has 1 valence and chlorine has 7. So sodium wants to get rid of that 1 valence electron so it falls back in energy level, which makes it stable. And chlorine wants to gain 1. So that's what happens. That's that transfer of electrons. There's a big electronegativity difference between these two. Chlorine's very high, sodium's very low, and the electron gets transferred. So when an electron gets transferred from sodium to chlorine, you can see we've formed the chloride ion. Now we have 18 electrons and 17 protons. So it gets larger. Remember that anions get larger. They're larger than their parent atom. So here's the parent atom, and you can see that it gets larger. Now here is the sodium ion. It now has 11 protons and 10 electrons. So it gets smaller. It falls back a whole energy level. The 1 valence electron is in a higher energy level than everything else. Okay, and it's this electrostatic attraction, the Coulombic attraction between sodium at a plus 1 and chlorine at a minus 1 that holds this together. And one thing that's unique about ionic substances, they really aren't independent. Like a water molecule, things that are held together with covalent bonds, it's pretty independent of everything else. An ionic compound is a lattice or a crystal where you have intertwining positive and negative charges. And you can see the sodium chloride crystal that is right here. Okay, so what the simplest unit is that we get that compound and establish that compound is what's called the formula unit. So that's the simplest collection of atoms from which an ionic compound's formula can be established. So a crystal of sodium chloride may have millions and millions and millions of sodium ions and millions and millions and millions of chloride ions. However, we just report the simplest ratio, which is 1 to 1. Okay, so here's NaCl. Now with calcium, you need 2 chlorines to establish that formula unit. And here with sodium and oxygen, you need 2 sodiums and 1 oxygen. So we're going to look here at these examples on how do we actually show the formation of an ionic bond. And we're going to do it with these 3 examples that are right here. So I'm going to flip to the next page. Okay, and I drew these out for you. There's always 3 steps, and the 3 steps are very formulaic, very similar. Okay, so this is the first one for NaCl. So you write the 2 or 3 or however many ions that you have next to or atoms, next to each other. So sodium, it's in group 1, it has 1 valence electron. Here's chlorine, it has 7 valence electrons. So I kind of think of it as it has a spot for an extra electron, and sodium's trying to get rid of this. The goal here is to get rid of all the valence electrons for the metals and to fill up with 8 the nonmetals. Okay, so we kind of draw an arrow here to show where is this electron going to fill in, where is it going to be transferred. Okay, that's always step 1. No charges are shown. The electrons have not been transferred yet. They're both neutral atoms. In step 2, this is where we show the electron transferred in our formation of ions. So sodium has lost 1. And when it loses 1, it gets a positive 1 charge. Chlorine has gained 1. It has an extra electron. As you can see, it has 8 around it. Okay, sodium actually does have 8 around it as well, but they're just back in energy level from its valence level. So chlorine has 8. It has an extra 1, so it has a -1 charge. Okay, then lastly, and this should have a plus, I should have wrote this down. This should have a +1 and a -1 right here for your final formula unit. Let's see if I can write that in. I'll probably mess it all up. Let's go with the pen. And so this is going to be a plus. Oh, it's red. Plus and minus. There we go. So that should be shown there, right there, for sure. Okay, that you have that +1, -1. These two, the actual example and step 3 should match each other, with the exception of having the charges shown in step 3. This is actually the formula unit that we call right there. Okay, so the next one, CaCl2. So calcium's in group 2. It's an alkaline earth metal. It has 2 valence electrons. Each chlorine has, again, 7. It wants to gain 1. So that's why the formula for calcium chloride is CaCl2. Because if calcium loses 1 to 1 chlorine, it's not going to be stable. It needs to lose 2, so you need another chlorine to do that. So 1 electron is going to get transferred here. 1 electron is going to get transferred here. You could write these side by side. It really doesn't matter where you write them. Okay. And then in step 2, we show each of our atoms. We don't consolidate yet with subscripts or anything like that. We have a calcium that's lost 2, so it has a +2 charge. And we have 2 chlorines with 8 apiece, but 1 extra. And they each have a -1. So overall, our charge is equal and opposite. Here's -1, there's -2, and then there's +2. Okay. And lastly, now we put it all together into our formula unit. You can use a subscript for the 2 chlorines that are exactly the same. So we have Ca at a +2 and 2 chlorines at a -1. Note this isn't a -2. You don't have 2 chlorines at a -2. You have 2 of them each at a -1. And again, this matches exactly what your original substance was, except with the charges shown, your +2 and your -1. Okay. And lastly, your sodium oxide. You can kind of think from up here, sodium has 1 valence electron each. You need 2 sodiums, and oxygen has 6 valence electrons. Okay, so the sodium is going to transfer 1 to this oxygen, and this sodium is going to transfer to the same oxygen. Oxygen needs to gain 2. That's why you need 2 sodiums in order to do that. That's why sodium oxide isn't just NaO, because sodium only has 1 to give. Oxygen has 2 that it needs to gain. So in our step 2, sodium that's lost 1, Na+, sodium that's lost 1, Na+, oxygen that's gained 2. So it's a -2. As you can see, it's filled with 8. Remember that the goal here is for the metal to get rid of all of its electrons and for the nonmetals to fill up with 8. And then lastly, here's our formula unit. We can consolidate these two. We have 2 Nas at a +1. Note, not a +2, a +1. You have 2 of them at a +1, and your oxygen or oxide at a -2. So these two match each other. So you're good to go. Okay. So for your homework tonight, you're going to have to do 4 of these. And you can follow this format. You need to show all 3 steps. First step, draw your arrows where you're going to transfer. Step 2, show all of your atoms with the charges shown. And then finally in step 3, your formula unit, consolidate so that you have matching what your example was, except with the charges shown. Okay. So we're going to go into a couple other things real quick just to kind of wrap up 6.3. The main thing is writing those structures, okay? But some characteristics about ionic bonding, just in general, ionic bonds are stronger than covalent bonds for the most part. That attraction between the positive and negative ions is very strong. In an ionic crystal, ions minimize their potential energy by combining in an orderly arrangement. This is called a crystal lattice. These 3D arrangements of ions and the strength of attractions between them vary with the sizes and charges of the ions and number of ions with different charges. This is based on Coulomb's law. And Coulomb's law, just to kind of break it down in a little bit easier than the actual law itself, basically states that the greater the charge between the opposite charges, the stronger that force is, and the closer you get them, the stronger they are. So very strong ionic bonds have high charge, like +2, -2, +3, -3, and they're really close together. They're small ions, okay? And to compare bond strength in ionic compounds, chemists compare amounts of energy released when ions form from a gas into a crystalline solid, okay? And that's called lattice energy. So that's sort of our next thing we're going to define. This is just showing you a crystal lattice. This would be like NaCl. This is a very simple unit cell, okay, of +1 and -1, or it could be +2, -2, and +3, -3, okay? And here's that term lattice energy that I mentioned. This is how we measure the strength of an ionic bond. With covalent bonds, we just use what was called bond energy. For ionic bonds, you use lattice energy, okay? And that's the energy released when 1 mole of ionic crystalline compound is formed from its gaseous ions. There's a table, table 3 on page 193 that goes through a bunch of these, but just to show you too, the negative value here means that energy is being released. That's it. That's just showing you direction, okay? So this MgO, this negative 3,760, means there's more energy released when it forms than compared to KCl. So we would say that MgO has a stronger ionic bond because more energy is released when it forms. So if you had to break it back up into Mg and O, you would have to input more energy to do that. The reason of this great difference is MgO is +2, -2, and KCl is +1, -1. So the +1, -1 isn't quite as strong as +2, -2. Plus MgO is small, smaller than KCl. So it is a larger value in terms of lattice energy. Okay. And now lastly, just a quick little comparison between ionic and molecular compounds. Okay. And this first one is ionic. We're going to go through ionic here. It's usually formed between a metal and a nonmetal. Okay. Ionic compounds have very high melting points because of their strong bonds. They do conduct electricity in the molten state, meaning when they're liquefied, and in solution when they're dissolved in water, because they break up into ions, and those ions allow a current to flow. Okay, they are soluble in water. Most of them do dissolve in water. There are some that aren't, but for the most part, ionic substances are soluble in water. Okay, and they're very hard but brittle. They're crystals. If you would strike them with a hammer or something like that, they would shatter. All right, now here's your molecular compounds. They're formed between atoms of nonmetals. They have low melting points, okay, because they're pretty much independent of one another. There are what we call intermolecular forces. We'll look at those in 6.5, but basically those are much weaker than a bonding force. Okay, they do not conduct electricity. They're not made up of ions, so they don't conduct in any state. They're usually gases at room temperature, again, because they don't hold together very well. They're independent particles. Okay, so in your notes, there's even a diagram there that shows you an ionic substance and shows you water for a molecular substance, but they are very different. Okay, and finally, like I mentioned, this bond forms molecules such as H2O. Okay, well, that sort of brings us to the end of 6.3. Okay, like I said, for your homework, you'll be drawing some ionic structures, those 3-step to showing how those bond and form those formula units. So if you have any questions, let me know.